Right, let's start. So last time at the end of our class we discussed about how to solve this matrix factorization problem using block coordinate descent framework. So if we are given this matrix, which is just general rectangular matrix, although this matrix appears to be square matrix this time, but it is of course rectangular matrix, and this kind of factorization is called a low rank matrix factorization. And then we want to make it as close as possible, so we are just formulating this as A minus WH, okay, and this Frobenius norm squared, which is the difference, element-wise difference between these two matrices, and then take the square of these element-wise differences and then sum them up, and that is the definition of this Frobenius norm. So we want to minimize this with respect to W and H. And so last time we discussed about fixing, for example, W and then solving for H, and then fixing H as that updated solution and then solving for W, right? So we iterated over these two steps, and then that can be viewed as a block coordinate descent. Okay, and so if we fix this this part, and then even though H has many different elements, like 2 rows and 4 columns, but from the column combination perspective of a matrix multiplication, the first element is a linear combination of these two by using these two linear combination coefficients. And so that the first column of H will be involved to form the corresponding first column, and the second one will form the second column, and so on. So 4 columns we have in W is completely decomposed into 4 independent optimization problem, right? So we just split them into 4 columns, and the first column is approximately the same as the W, the entire matrix W times first column of H, and then second column is also represented as the entire matrix W and the second column of an H. And so that way we are solving for the independent least squares problem, because in that case, in this case, this column can be viewed as B, for example, and then if we just rewrite W and A as A, and then we denote the first column of H, and then as an X, and then we are solving for these 4 different least squares problem, and we know how to solve this equation, and that is through the normal equation, right? And so that's how we can obtain the optimal solution. But we are considering the non-negative matrix factorization that additionally has this non-negativity constraints on each element of W and H. So in this case, what if we have non-negative elements as our optimal solution for W? So in that case, how can we satisfy our constraint to be non-negative? So in this case, as I mentioned, just simply clipping and making all non-zero values into 0 to satisfy non-negativity constraint, that is no longer be the solution or optimal solution for our non-negativity constraint least squares problem. Okay, so in order to solve this problem, there are many different methods. But one method that I want to describe during our lecture is changing this kind of problem of matrix factorization into sum of rank 1 outer product. Okay, so in this case, so if we have W and H in this form, and then we can think of this product of W and H as the sum of the rank 1 outer product. For example, this column and that row, and the second one and the second row, and maybe let's consider the rank 3 case. Okay, and then so this matrix is this guy and that guy, and plus and another one, right? So this is rank 1 outer product perspective of viewing this matrix multiplication, right? And so we want to still make this guy, right? And then so let's call this as W1, W2, W3 as 3 columns, and the H1 transpose, H2 transpose, H3 transpose, indicating the rows of our matrix H. And in that case, this guy can be viewed as A minus I is equal to 1 through K, where K is 3 this time, and Wi and Hi transpose, which indicates each outer product component, right? Okay, so in this case, so let me just finish the last one. Yes. Like 3 guys. Okay, so here now we can see 6 different variable blocks, and so we still apply block coordinate descent, but we now change our strategy of partitioning or forming our blocks out of these many variables into 6 pieces. So first, second, third, and fourth, and so on, right? So instead of just forming only the 2 blocks, we now apply 6 block based block coordinate descent. Okay, and then so let's consider solving for this block, okay, for example, and then all the other blocks will be in the beginning we will just randomly initialize them, or in the middle of our iteration of our algorithm, they will be updated at a time when viewing particular components or variable block as our really variable to optimize. So in this case, this part is fixed, and this part is also fixed, right? Okay, so in this expression, let's just subtract first these 2 components, which doesn't have any variable at all. Okay, so we can easily form the outer product of them, and then just to subtract these 2 outer products from A. So A is constant, and the latter 2 is also constant. So the remaining part will also be a constant, right? And then let's denote that remainder of our matrix as R. Okay, so more exactly, R is A minus W2 H2 transpose minus W3 H3 transpose, right? So these are still constant. Okay. Okay, then suppose this matrix is maybe 2 by 3 matrix, and this guy is maybe 1 2 3 4 5 6. This is just an example of remainder R. And by the way, this so this remainder R, let's say it can possibly have some negative values as well, in case the corresponding elements of these two may be larger than the original element, I mean corresponding element of an A, right? So you can, this matrix R is involving a negative component as well. Okay, and then here, so we just subtract this part. Only one rank on our product. And then again, this part is still fixed as well. So these are just known constants at this time, because we are only viewing that part as our variable, right? Okay, so this guy, because this guy will satisfy our constraint to be non-negativity, I mean, so let's consider that element as maybe 2, 3, 4. Okay, so this is corresponding to this guy. Okay, and then this part will be this guy. Let's call that as an x and y, for example. Okay, so these two elements are those variables to optimize it this time, right? Any questions so far? Okay, then if we just let's see. Oops. Okay, so let's just rewrite it. Then it is 2x, 3x, 4x, 2y, 3y, 4y, right? And then let's just take the subtraction and then take the square of it and then sum them up. And then that will be, so I'll just change the sign within the parentheses to be squared. 2x minus 1 squared, 3x plus 3 squared, 4x minus 5 squared. Okay, so that is the part involving x. And then the latter part corresponding to the second column is 2y minus 2 squared, 3y minus 4 squared, right? Okay, so this part and this part is completely independent, because the first part is involving only x and the second involving y as well. And so the optimization for this expression can be done easily by using the quadratic form. I mean, in this case, 29x squared minus 22 x no 26 right, and something, right? Okay, so in this case, what's the optimal value of an x? So we just simply apply the formula of 29 times 2, this guy, right? So this is our optimal value of an x, and we can also obtain y. But what if our expression is something like this, which has the axis of our 파라볼라 포물선 영어로 뭐죠? 파라볼라 맞아요? 포물선? 맞아요? 파라볼라가 단수예요, 복수예요? 네, 단수예요, 복수예요. 이게 파라볼라스예요. 그죠? 보통 A가 붙으면 이게 복수일 가능성이 좀 높은데 로컬 미니멈, 미니마, 파라볼 럼이라고는 하진 않으니까 파라볼라가 단수일 것 같은데 어쨌건 네, parabola, right? And then we consider axis, and that axis and the corresponding x value is our optimal value, right? But in this particular case, this is an x, and this is our function to optimize. But here, yeah, it's something like this, where our axis is placed at the negative part, right? But here, we have to satisfy our constraint of non-negativity, right? So our feasible set, our feasible region is this part, right? So in this case, what is our function? Our function is only this part, right? So in this case, what will be the optimal x? Optimal x is 0, right? 0. So in this case, if the solution for this, for unconstrained optimization problem is, is having a negative value for our optimal variable, and then we can just simply clip it to have 0 value. Okay, so in this constrained optimization, where x is always greater than or equal to 0 in this region, and then by looking at the shape of our objective function, the minimum value is achieved when the x value is 0, right? So this is the optimal solution, even when considering the non-negativity constraint. Okay, so similarly, we can obtain the solution from the next part, from the second part for y, right? So here in this case, we just obtain the unconstrained version of the optimal solution, and then for each of the negative values, we can just simply set it as 0, right? So that is still our optimal solution for the unconstrained version of an optimization problem. Okay. Okay. So we studied, or we discussed how to optimize this part, right? And then how can we optimize this part? So here, if we have a more than 2 blocks in our block coordinate descent, the order really matters. So we can follow this order, 4, 5, 6, okay, or maybe this guy, and this guy, this guy, this guy, this guy, this guy, right? So this order, the block coordinate descent algorithm does not originally specify any constraints or any specifications on particular order. So order, I mean, we can freely choose our order, but in general, once we choose a particular order, I mean, fix the order, and then we just follow it throughout the entire iteration. So if we follow this order, and then in the next iterations, we will also follow that order. Regardless of any orders, this block coordinate descent and their theoretical kind of foundations will guarantee that we will just reach the local minimum. Okay, and let's suppose we want to solve this guy, and in this case, I mean, that is also almost the same. In this case, so maybe, so this is maybe 2 and 3, and x, y, and z. Okay, so in this case, yeah, we can also simply rewrite this part 2x, 2y, 2z, and 3x, 3y, 3z. Yeah, and then do the same thing. And then for x and y and z, it will be just univariate second order optimization problem. And so yeah, we can also easily obtain the optimal value of an x, y, and z. So once obtaining these values corresponding to this green part, I mean horizontal row vectors, and then using that, we can also update this part as well. And then now, yeah, let's move to this guy, and then we subtract this part and that part from the original A, and that's how we form this R. And then, yeah, using this fixed column vector, we can update that pink row vector as well, right? Okay, so so this is how we perform this block coordinate descent by using 6-block based setting. So last time in this least squares problem, I mentioned that, where is it? So in this least squares problem, where we have to solve for this part jointly, okay? So in the case of 2-block case, even though we can split them into 4 independent least squares problem, but for each sub problem, if we have to solve for the first column of an H, and then we have 2 variables, and these 2 variables cannot be separated into like unimodal or univariate optimization case, because in that case we have to handle that as a vector as it is. So that way we have to form this least squares and the normal equation, right? So when solving this x, we have to handle this linear system where we can optimize this x jointly among these different elements contained in x, right? So that's why once obtaining the optimal solution as, for example, 3 and -1, and then if this guy is replaced by 0, and then this is no longer be the optimal solution. We have no guarantees about it. And in general, that kind of solution is no longer be an optimal solution for the unconstrained version of this least squares. Okay, but in this case of rank 1 outer product perspective, and then even though we have to solve for multiple variables at a time, I mean simultaneously, but once evaluating this expression, it's all decomposed as a univariate optimization problem. So over here and over here, so x and y are now no longer be mixed together, right? We can completely separate them into really one-dimensional or univariate optimization case. Okay, so in that case, we can easily think of their optimal solution, even when considering the constraint of the non-negativity. Any questions? So at a high level, when solving for this NMF or this matrix factorization, has several different optimization strategy or algorithms. So the first one, I mean, yeah, we discussed about the gradient descent in this problem. So when applying the gradient descent, we we handle all the variables simultaneously at a time, right? So in that case, we just compute the partial derivative with respect to this element and this element and this element and so on, right? All these partial derivative with respect to each of these variables, right? And then by using the step size, right? Step size. So by using a particular step size, we just update all these variables with a small amount, right? So that's how we apply the gradient descent. And so we can utilize that gradient descent, but in this case of a constrained version of the optimization problem, so we have to consider the feasible set where the possible solutions exist, which is literally that all the variables should remain non-negative, right? So how can we obey or satisfy this kind of constraints while performing the gradient descent, right? So that way, although I haven't discussed the full details, but in that situation, we can apply the projected gradient descent, right, to make all the intermediate outputs during our iterative updating steps to satisfy our constraint, right? So at a high level, we have that strategy of applying gradient descent, and then the second second strategy is to apply this block coordinate descent. But for this block coordinate descent, we have also choices or options with respect to like how to form our blocks, right? How many blocks will we have? Okay, and also at an extreme, we can actually split or form our blocks in our block coordinate descent into a single variable. Okay, just a single variable. So we just update this value while setting all the other values as constant. Okay, and then we can similarly perform the updating on that value, by just evaluating all the known parts, right? So in that case, it is called a coordinate descent, not a block coordinate descent, because our each of our block is involving only a single variable, right? So that is corresponding to coordinate descent. And especially in this NMF, I think I showed maybe some of the Nature papers about this NMF, and the particular algorithm proposed in that original NMF paper was based on this single variable block based block coordinate descent, and that is also called the multiplicative updating. So the initial algorithm originally proposed in that one of the early stage NMF papers was this algorithm, multiplicative updating, and they have their own derivations on their algorithm, but at a high level they follow this single variable block coordinate descent. Any questions so far? Yeah, and in general, what will be the difference depending on the block size that we set when applying the block coordinate descent? So we considered like 2 block coordinate descent by just setting 1 and then second, and then we considered, in this case, based on rank 1 outer product, if we set the target rank as k, and then it is how many blocks we have, it is 2 times k blocks. Okay, so in this case 2k block coordinate descent, right? And then at an extreme, if we set just a single variable as our individual blocks, and then it is like how many blocks do we have? Like m by k plus k by n block coordinates, right? Because we have that many elements. So in general, if we set a bigger blocks involving more variables at a time, and then solving that subproblem will usually be more difficult and more complex. So as I mentioned, in this least squares problem, I mean, yeah, we also have, we can also solve properly, correctly, this constraint version of the least squares problem, called the non-negativity constraint least squares. Okay, so in that case, by satisfying this non-negativity constraint, we can actually solve for this least squares problem, and that is based on like those active and passive set of variables. Yeah, so their main idea is, right, yeah, so it's really about the optimization theory, which I'm not fully familiar with. So this is typical least squares. So let's use another. So it's a definitely overdetermined system, and this is our variable. And here, so we have three variables, right? And then in the optimization theory, so we can actually partition or split them into two sets of variables. One is active set, and the other is passive set. Okay, and active set is actually those variables that are stuck by our constraint. And yeah, so suppose our feasible set or our constraint for our input variable is some regions like this. Okay, so in the case of NMF, or this non-negativity constraint least squares problem was our feasible set. So in this case, so it is like the first quadrant, right, where each of our variables are all positives, right? So that's our feasible set. And then in general, we can think of this arbitrary feasible set, right? And then active set of variables is like for those three variables, one variable is actually hitting the boundary. Okay, so in our non-negativity constraints, so these are feasible set where x, y, z, right? And then so if our solution, optimal solution is really like this vector, and then y is actually hitting the boundary currently at an optimal solution, right? So in this case, this guy is active set, and x and z is corresponding to passive set. So the entire variable entire variables are partitioned into active and passive sets when considering the optimal solution. Okay, and in that case, there is a theory. I'm just give you, or I'll just briefly introduce the theory that is used to solve this non-negativity constraint least squares. But the theory says, if we know in advance what is a passive and what is an active set of variables, okay? So if we have 100 variables, and then suppose we know already which are active and which are passive variables, okay? So in that case, assuming that we know those partitionings exactly, and then the actual optimal solution is obtained, is computed, or that actual optimal solution is equivalent to the solution of this problem. So if we know this guy is becoming 0 at an optimal solution, and then by the fact that this guy is 0, and then we can think of their reduced version of the least squares problem, where we just bring these two columns over here, okay, and then xc, for example, okay, and then minus the original vector b, okay. So this is a kind of a reduced least squares version, because we just simply discarded or removed the active set of variables, which is just a 0, and so multiplying the second column by 0, they will have no effect, so we might as well just remove them, okay. So in this case, this is the smaller version of least squares solution that only involves the passive set of variables, okay, passive set of variables. And then let's imagine just solving this with no constraints, okay, as an unconstrained version of the problem, okay. And then that solution, okay, that solution will be guaranteed to have positive values by the fact that they are already known to be included in the passive set that doesn't touch these boundaries, okay. So they are somewhere over here, okay. So in this case, so if we just only choose the passive set of variables and then solving this problem as an unconstrained problem, and then all the solutions will be strictly positive, and we will, it is impossible to observe negative values in our optimal solution. And so if it isn't negative values, and then somehow it is violating our condition or our assumption that we already know the exact partitioning of into this active and passive set for our optimal solution. So so we have that kind of nice theory in the optimization areas. And so and so at a high level, once we know this active set passive partitioning when considering the optimal solution, and then we just form this smaller problems and then solve for the unconstrained version of the solution, and then those values will be just an optimal solution for this x and c in original constrained version of constrained optimization problem, okay. So in that case, the problem is, what's the problem? So the problem is, we do not know which variable is active and passive sets, right? Because which one is active or passive is determined only based on the final solution is final solution, the true optimal solution. But we don't know the true optimal solution, right? So we have some other hopefully interesting optimization technique that can actually adaptively change this active and passive set. So we randomly partition the set of variables that we are given into active and passive. Of course, partitioning means no overlapping, and then considering the unions, that will form the entire set. So in that case, this is a temporary partitioning that is not necessarily following the ground truth, and so only using the passive variables, and then we solve for this smaller version of the least squares, and then check whether we have negative values in our solution. And then if we found the negative solution, and then this partitioning to start with is wrong actually, right? And so in that case, we adjust. Yeah, we have some algorithm that guarantees monotonic kind of improvement in our optimization problem, and then we adaptively change our active and passive sets. Okay, and then we form the new version of the small problem by only using the newly updated passive variables, and then check for the solution and determine whether that is violating any of these conditions to be non-negative and so on. So that is that is called the active set based algorithm for non-negativity constraint least squares. Okay. So personally, or actually my advisor at Georgia Tech, she was really she's a really expert on these optimization algorithm, and so yeah. Any questions? Okay, then let's move to a little bit more advanced version of this matrix factorization problem. So I'd like to introduce and discuss how to solve for this advanced or another variant of this non-negativity constraint matrix factorization problem. So here, yes, we discussed about the application of NMF in the topic modeling, right? So if we are given this term document matrix, and then when applying the matrix factorization on this matrix, and then so these are terms and these are documents, and then the left matrix and each column in the left matrix can be viewed as a topic, and then the first column has the large component corresponding to these democracy and the president and so on. And so roughly we can understand that first topic is about the politics, and then the second topic derived in this form. I mean, let's suppose these two topics are optimal solution after we perform block coordinate descent. And then the second topic is having a large component in the AI and the science terms. And so those guys are the major terms in the second topic, and thus we can see that the second topic is related to the science or AI. So and then we can think of this matrix H as an indicator for the soft cluster membership. So the first document, if it is if this vector is 0.8 and 1.1, and then it is saying the first document is having the first topic with the weight of 2.8, and then the second topic with the weight of 1.1, and so the first topic has a higher weight with the first topic, right? So that way the first topic is more related to the politics, right? And so if we have more topics, more number of topics, and then if we choose the largest element and its corresponding topic, and then we can just obtain the hard clustering membership from this matrix factorization result. Okay, so that way we can apply the topic modeling or matrix factorization to the term document matrix and obtain this nice visualization. So each document is represented as a single dot, and then so we see 10 different clusters, and so we obtained 10 different topics. So we set K as 10 and applied or computed matrix non-negative matrix factorization on this term document matrix, and then each column in our matrix W, and then we chose the largest element, yeah, within this first column, and then chose the corresponding keyword, the corresponding dimension and its keyword. And then the second topic, we did the same thing, and then that's how we obtained these major keywords or representative keywords of each clusters. So this is a car review data set, and this one is about Hyundai Genesis car model and its review data set that I collected in maybe 2013. So in that case, yeah, and also if a particular document is clustered into this cluster, and then we just, yeah, in terms of the largest entry in the corresponding column of an H, okay, so that's how we just color coded each document. And then this 2D embedding plot was obtained, some variant of TSNE that I used in this work. And so this guy is about series Zera and compare, and so this one is about the comparison. I mean the topics where people compare this Genesis with the another car model called Zera. This guy is, by the way, American's car name of a grandeur here in Korea. And then maybe economy, fuel, and GPS is another topic that people are discussing. And this is a tire, and Dunlop is a tire brand. And this one is talking about the color. And this one is comparison against the Lexus and Chrysler, and so on. And then this one is another topic about some potential issue on this car, possibly related to gear shifting system. Okay, so this is how we can perform the topic modeling and visualize the result. And then did I show this example? Okay, so this is a TV review data set that we discussed. And then this is these lists are the sorted keywords and their weights for a particular column in our W corresponding to this topic. And then this topic is having the dominant keywords of a television and excellent and product. And so here, we can actually modify or manipulate those keywords weight. And so here, what I did was to remove the first keyword television because it's all about the TV data set, right? And so we can remove it. And then instead, I just increase the weight of this the keyword weight corresponding to recommended. So I just pressed a few times of a plus button, and then this is the newly updated or modified result after performing the topic modeling on this user feedback. Okay, and then I'll just skip the rest of the story, but this is the algorithm to perform this semi-supervised topic modeling or clustering algorithm from the non-negativity matrix factorization perspective. So let me just explain a little bit on this. And so we have this original criteria and non-negativity constraint, right? And then here, let's consider the first regularization term with some hyperparameter alpha, and then so we have A is Okay, so we have 3 documents and 4 keywords, right? And so we have this Frobenius norm squared to minimize, okay? And then suppose the topic that we manipulated, just like what we saw here, like this. So suppose this one is the first column vector of our W, okay? And then after solving this non-negative, NMF, suppose this guy was 0.3 and 1.5 and 2 and 0.7, okay? And then suppose we just replace this guy as 0, okay? Similar to what we did in here by just removing this television keyword, and then we can think of this situation as setting or replacing this value as 0. So in this case, how can we update our NMF result based on this feedback? So what I did was we have this replaced or user manipulated, or this manipulated column of W, right? So here I just simply added another regularization where the first column of W, let's call W1, okay, as the current one, 0.3, 1.5, and 0 and 0.7. Okay, so here we can use 2 norm or 1 norm, and then we can have this kind of regularization, right? And then we can softly or weakly force this W1 to be close to this value, right? But in general, it is a little bit difficult to only form the user manipulated column. For example, we didn't touch upon this second column at all, right? So here what we did was, instead of using this guy that may have a different size of our matrix or different columns that we chose, so I just so here I just set it as this guy. So this is W, and this is a user defined W, so that is called WR, and I just set any value over here, and here we can just mask out the difference of the second column. And so here we can just scale or apply the scalar multiplication on each of different columns. So in terms of the first column, we can apply maybe 1, and then for the second column we can apply just a scalar multiple of 0, right? So this mask matrix is playing that role. And what should be the size of MW where we multiply over here? So in the linear algebra, suppose we have this matrix, and then we want to scale the first column by 7 and the second column by 8. How can we represent this column-wise scaling by matrix multiplication? So the column-wise scaling can be represented as this multiplication with diagonal matrix on the right, right? So in this case, so we have 2 columns, and then the first linear combination coefficient is 7 and 0, right? So that way we obtain 7 times 1, 3, 5, and this is our first column. And then the second column is 0 times 8, 0 times 8, and so 8 times 2, 4, 6. So this is how we can easily perform the column-wise scaling. And similarly, if we want to perform the row-wise scaling, and then we just multiply over here the square matrix, square, of course, diagonal matrix on the left, and then maybe 1, 2, 3, and then that will correspond to scaling each column by respective element. So here the MW is 2 by 2, and here 0 and 1, 1 and 0, and this is our mask matrix. So what if we touched upon, what if we manipulated the second column as well, or second topic, and then this one will be set as the user manipulated result, and then this guy will be 1, right? And then if it is a larger matrix, and then you guys know, get the idea, right? So we just starting from the identity matrix multiplied on the right, and then we just set one only for those topics that users users are involved to change those values. So that is this term. Then also, see, so this is a little bit more complicated case involving more and more variables, number of data items. So in this case, the corresponding operation is actually to merge the two different clusters. Okay, so over here, let's see. No, not this one. Okay, so trees and the hierarchies and so on. And this orange one, tree maps and layout and hierarchy, and trees and hierarchy and node, and those two are seemingly quite close topics. So we can just merge them together, right? So in this case, we can also manipulate those elements in our W and H. So how can we perform this cluster merging in the perspective of this matrix factorization? So we can actually, suppose we merge these two, and then what would be the reasonable initialization of the merged cluster of the two? So we just simply add them, take the average element wise, and that's how we obtain the average centroid between the two clusters, right? And so once obtaining or removing this guy into a single centroid vector, and even though we have two clusters over here, and then reducing or merging two of them into one, and then we will only have a single columns. But if we have in general k columns, and then suppose merging two of them into one, and then we have k minus 1 columns now, and then this part should also change as well, or this cluster membership part of our document should also change as well, because we have a 1 column reduced, and then over here we have the corresponding cluster membership to these two of these clusters to be merged, and so we can simply add them together because they are just a the cluster membership into two, and so when they are merged, and then it's reasonable to just add them into a single value. Okay, so that's how we can just merge those two corresponding rows in our H part. Okay, and then we can also support some splitting as well. So if one cluster is a little bit ambiguous, so dimension and multivariate and parallel, and then if we split them into two, and then we just provide initially two of the duplicated column vectors, and then from here we can actually make the we allow users to create the differences or changes between the two. So in the case of high dimensional or multivariate data analysis, by the way, these are the paper collections or research paper collections published in, I think it's in the visualization area, because I just submitted it there. And so here initially starting with the duplicate topic proportions, and then in one cases I just increased the weight of dimension reduction topic, and then the other part I just increased the weight of the term clusters. So I just manipulated these cluster splitting in a way that the first split cluster is corresponding to the dimension reduction as a specific subtopic of this dimension and the multivariate and the parallel and so on, and the second topic is mainly related to the clusters. Okay, so in this case we can split one of them into two, and then we just bring them into the regularization part in our W, like this part, because we set our meaning of the two of these split topics, and then we include those columns into this regularized part, and then we also increase another row in our cluster membership part, and then continue our iteration in our NMF using this new settings of having another additional column in our W due to this cluster splitting, and another row in our H part as well. Okay, so that way we can generally perform many different user manipulations in the middle of this topic modeling optimization based on this block coordinate descent and so on. Any questions so far? Okay, then let's take 10-minute breaks, and then resume at 4:46. 네.
클러스터링 저 교수께서 보여주신 그 카리뷰
네.
그러니까 웨이트를 서로 다르게 주면서 그거에 나타나는 상관관계가 분석된 그런 툴인가요?
그렇죠. 네. 네. 이거 옛날에 이제 했던 연구인데 툴인 게 맞고, 근데 지금 공개를 하거나 그렇게 되어 있지는 않고요. 웹상으로 이렇게 좀 만들 여유는 없었어서 저희 좀 여러 좀 디펜던시가 좀 복잡하게 있는 좀 그런 로컬 툴이에요. 자바로 만든. 네.
저그 인턴 연장이랑 진로 상담 관련해서 면담 신청해볼까요? 언제 시간 되세요? 되게 바쁘시잖아요. 항상 꽉꽉 차 계시던데.
밥은 언제 먹어요?
저요? 저 끝나고 수업 끝나고 바로.
언제 밥 먹고 오나요?
저 밥 먹고 그냥 계속 연구실에 있어요.
근데 7시 반쯤 오나요?
네?
7시 반쯤 와요.
아 네네네.
그럼 그때 먹어요?
아 네네. 교무실 그 교수님 방으로.
네네네.
아 네 알겠습니다.
프로젝트 언제까지냐고요? 그 모의고사 시작하는 직전 일요일? 네.
한 18일쯤
그럴 거예요. 네.
근데 일요일에 올라오긴 안 돼. 아니 아니. 18 그게 아침 잘 뻔. 근데 그 이날은 내가 정해야죠. 가서 할수 없는 거 같아.
그때는 제일 짧은 선배의 딜이 있겠다.
아 근데 원래 진짜 도민할 때
호환 잘 돼 있어.
위치가 없잖아. 그게 아니야. 그건 전화를 해서
잘 높은 애 좋아하지.
아 생각을 안 해. 예를 들어서 이런 방식이
이거 리퍼런스 가만히 없어.
교수님 오시면 바로 아까부터 그러니까 다섯 번 오케이 실험은 진행되지 않아서 다른 데스크를 준비했다. 맞아요. 알지. 뭐하냐.
근데 착각해서 쉬는 시간 좀 일찍 가졌네요. 1시간인 줄 알고 왜 그렇게 생각했지? 계속 해야죠. Alright, so let's start. So yeah, in this case, we discussed about user intervention on on the topic itself with respect to their keyword weightings. But we can also apply this user intervention in terms of the data item level. So we consider the example of user intervention over here on the W part, but we can do the similar thing on the H part. And so typically in the literature of clustering, I mean this is a part of or an example of something called semi-supervised clustering. So semi-supervised clustering is that clustering is by default unsupervised one, but those semi-supervised one is adapting or incorporating some of the additional user feedback and so on. And so another user intervention can be done in the form of I mean the most standard form is must link or cannot link. So must link and cannot link is the notion defined on the data item level. So the idea is simple. The two of data items should be linked together. So that's the meaning of must link. And in other words, those two data items should belong to the same cluster, and the two other data items should not belong to a single cluster. So that can be viewed as a cannot link. So there are many studies on how to perform this semi-supervised version of the clustering, and depending on a particular base clustering algorithm, there are many different algorithms. So one of the example of semi-supervised clustering is applied to the k-means to reflect this must link and the cannot link constraints. And so here, how can we perform this cannot link constraint in this matrix factorization case? So we can also apply this must link in this form. So suppose we have this matrix as an H. So if we have 100 columns in H, and then it means we have 100 columns, and then we have maybe 3 topics or 3 clusters, and then suppose this data item and maybe this data item should belong to the same cluster, and that is our constraint in the form of a must link. So in this case, in this case, we can also set their ideal values as, for example, so in this case, we have to also specify a particular cluster that data item 1 and 3 should belong to maybe cluster 2. And in this case, we can think of their ideal coefficient as a 0, 1, 0, and this guy is also 0, 1, 0. Okay, so in this case, we can set these two desired vectors for the first and the second data item, and then we can also apply the mask matrix based trick to only apply the constraint on the user selected data items. I mean, it is a really high level explanation, but you get the main idea about how to apply this kind of additional regularization to reflect different user interventions in the clustering or this matrix vectorization process. Okay, and then so this is a one example, and this is a kind of graph clustering problem. And so this NMF can also be applied, or this matrix vectorization can also be applied to this graph data setting. And then this particular example, I just collected all the actors and actresses and movie stars and maybe the TV TV show and those people appearing in these TV shows and music shows and so on. And then even if let me explain the input matrix. So input matrix is the similar to kind of co-occurrence matrix. If the two person co-starred or they appeared in the same TV shows or movies or whatever, and then we just count of these or frequency of how many the two of these actors or actresses appeared in the same shows. Okay, and so we can consider the undirected graph, which is the squared matrix. Okay, so if we have 100 different persons, and then it will be this square matrix. And then we can also do the clustering by using this matrix vectorization perspective. And then here we can, because this matrix is symmetric one. So what's the meaning of symmetric? Like this element at the 5, 3, and that is the same as 3, 5, right? Because the two persons appeared in the same shows, and then their frequencies are commonly recorded in these two elements. Okay, so there is no notion of the directionality in these relations. Okay, so in this case, because this matrix is a symmetric matrix, and so we can also think of the symmetric version of matrix vectorization. So the symmetric matrix vectorization, I mean, one of the representative example is Cholesky vectorization of like CC transpose. And then we can also think of this non-negativity constraint matrix vectorization in this case. Okay, so in this case, the fact that those two matrices are the same, so this guy is the same as this guy. Okay, so in this case, from this inner product perspective, so this is a fifth one and the third one, and that is producing this element. So this is a fifth and the third, and so those so this type of a inner product perspective can be also applied to the collaborative filtering and also word2vec and so on. But the main idea is this vector, those row vectors in the first matrix and the column vectors in the right matrix will provide the latent representation of our data item. So the fifth data item is represented as this vector, and the third data item is represented as this vector. But yeah, because these two matrices are symmetric, so the third column vector will be the same as the third row vector over here, right? And then yeah, once embedding these 100 different people into a particular dimensional space of maybe 10, and then we have 10-dimensional latent representation for each data item, and then once performing the inner product between the two, and then if the two vector and their inner product as a similarity, when viewing this inner product as a similarity, and then if the two data items have a large inner product based similarity, and then they probably co-stared or co-appeared frequently in the same shows. Okay, and then because we maintained or imposed non-negativity constraint, and then this guy can be viewed as a latent representation, but also we can interpret them into a clustering result. So we basically defined or computed 10 different clusters, and each value within one data item's representation is representing the cluster membership. So because we don't have any negative values or negative values, all the cluster membership will be non-negative or 0 or positive, which makes sense, right? And so by simply choosing the largest entry and then thinking just putting that data item into that corresponding cluster, we can also form the clustering on these 10 different clusters. So 100 data items will be clustered into 10 clusters. Okay. And by the way, in this case, this is viewed as a symmetric version of non-negative matrix factorization. But do you think whether this problem is easier or more difficult than the previous one of typical NMF, where we have these two different matrices of W and H? Which one is simpler to compute? Symmetric one? Non-symmetric one? So at least, let's think of the number of variables to consider or to optimize. So in this case, given the same matrix, we can still perform this matrix as this non-symmetric version of matrix factorization, where we have two factors of W and H. So in this case, it's 100 by 10 and 10 by 100, and so 1,000 and 2,000 is the total number of variables included in W and H. But what about this case? It is only containing 1,000 variables. So in terms of the number of variables, it is really half of the original non-symmetric version. And so in that sense, it might be easier. The symmetric one is easier, but in fact, this symmetric one is more difficult, because in the previous case, we can easily apply this block coordinate descent, right, by just separating our variable block into two, right? But here, when just applying two block coordinate descent, we cannot separate them because they are really the same variables, right? So we no longer can apply this two block coordinate descent. And also in the case of the 2K block coordinate descent or rank 1 outer product perspective. So in that case, we can view it as a rank 1 outer product of these column and row, and the second column and row, and so on, right? And then here, okay, so it is still possible, but in this case, let's consider this guy. And this green part and that green part will now be exactly the same, right? So in the previous case, one of them was fixed as a constant, and the other one is just solved using this second order polynomial. But here, so this one is no longer be a constant, right? So really, this guy is x1 squared and x squared and y squared and so on, right? Because sorry, it is wrong. So x and y and x and y, so it is like it's the outer product, right? And so this is an x squared and the y squared and xy and xy, right? So we cannot treat this guy as a constant, and thus these values is now the second order polynomial, and then we will have their own A matrix which is constant. And then if you imagine like this process, okay, then it's instead of 2x, it is just x squared, right? Because 2 in the place of 2, you will have an x, right? So in this case, x squared minus 1, and that will be also squared due to the Frobenius norm. And so the order or degree of this polynomial that we obtain is fourth order polynomial. Okay, so variables are multiplied between these two outer products, and that is already forming the second order polynomial or second order term. And then in the Frobenius norm computation, it will also be squared further, and so it will have a fourth order polynomial. And so in general, this symmetric version is more difficult to compute. But there are then in this case there are still a really nice trick. And then I think this trick is really useful, and then it can be hopefully applied to your research to increase or to make your contribution bigger. So in that case, let's consider this kind of problems as SC transpose. So S is our given matrix, just like A, and C is our matrix to compute or optimize. So in this case, we can represent, or we can change it into these two. I mean, we now treat these two matrices into really two different matrices instead of the same matrix. And that way we can circumvent or avoid having to handle this fourth order polynomial based on block coordinate descent. Does it make sense? But here, this is really no solution for this symmetric formulation. And now we can have this kind of regularization. Okay, so in this case, in the first original form, we have two different matrices where we can easily handle one by one in the block coordinate descent framework, and then we have additional regularizer so that the two matrices to be close to each other. Okay, so this kind of nice trick was actually utilized a lot in my lab to publish a lot of papers based on it. So this is one useful trick. I'm not sure it may be useful in the near future for your own research, but I think it's a really good trick to know. But anyways, back to this symmetric matrix factorization case. We discussed about how to obtain the clustering result, and then suppose this is an initial clustering result. And so how we obtain or how we visualize our clustering result in this manner, given this pairwise co-occurrence matrix. Okay, so in this case, okay, so these two guys, the third and the fifth person, co-occurred a lot in the same shows, and then those element will be really high, and then maybe this element is a high and that element is also high, and so on. Okay, so we can imagine, yeah, those highly co-occurring elements are found here and there, although they are all always symmetric matrix, right? And then yeah, based on the hard clustering result, so the third one and the fifth one and so on, and then let's consider the cluster index, their cluster index, by just taking the argmax. Okay, and then maybe the first one is, I mean, I'm just talking about the cluster index of each data items. So the first one is belonging to the second cluster, 5. Yeah, let's just assume we have a 5 clusters, 1, 3, 1, 4, 4, 5, 3, 1, and so on. Okay, suppose these are cluster index. Then and then, yeah, we just reorder those rows so that the first clusters are all appearing in the top rows. Okay, so we just bring these three rows, like this guy, and this guy. Okay, we just put it all the way to the top, and then in the case of second one, yeah, we also put them in the second block, and so on. It's just a matter of reordering of rows. And also we can do the same thing on the columns, right? And so, yeah, I mean, yeah, we do the reordering on this input matrix, okay, in this co-occurrence matrix, and then if we imagine this process, and then the first, I mean, those data items belonging to the first cluster will be all pushed towards the top, and then the second one and the third one and so on. Okay, and then we do the same thing on the columns as well, and then we obtain this kind of graph. So in the first people belonging to the first cluster, they will have large co-occurrence patterns within them, but no other parts in this other data items or other people. So that's why we see all blue values, which corresponds to 0. Okay, so that way, once performing the clustering on this graph-based representation of our data or co-occurrence or this pairwise relations matrix, then applying this reordering based on cluster index, and then we typically obtain this kind of result. And if we see many of these off-diagonal elements, and then it means we have no clear cluster index, no clear cluster structures. So even after performing the clustering, the data items in the first cluster and the second cluster still have a large overlap or high interactions or large co-occurrence patterns. So it means in that case, we have no clear clusters. But anyways, so this is what we obtained initially in the first stage of a clustering. But here we can see that there is a one cluster that is containing only one data item. Okay, and here let me see. When looking at or browsing through those people in this region or this second cluster, and then I found that these people are mainly singers. Okay, so those singers are probably co-appearing in many of these music shows. Okay, so that's where they co-appeared frequently. And then I found that those singers belonging to this big cluster is actually can be split into two parts. I mean, two groups, where the first group is American singers and the second group is European singers. And then I just chose a few of them and then did the supervision on and this kind of thing. So some of them, I just hard set or hard partition them, a few of them into the first cluster, and a few of them to belong to the second cluster. Okay, so some of them is assigned like this vector, and some of them is assigned like this vector. Okay, so depending, for a few American and few European singers. Okay, and then once giving this input in the form of this NMF with the regularization by involving user feedback, and then we obtained this kind of clustering where this big cluster is clustered further into these two parts based on this user feedback. Okay, and then here we can see that relatively high values on these off diagonal parts. So even if we split this big cluster into two, but among these two groups we have some non-trivial kind of values or similarities in terms of the co-occurring patterns. Okay, and then we can also see that like this guy. Okay, this guy, I mean, the corresponding row and the corresponding singer is actually having a large co-occurrences with the European singer, right? So that's what this large off-diagonal elements mean. And so we identified, examined, and what they are, and these are. I'm not sure if you guys are familiar with these people, but they are really famous pop singers in the US. Christina Aguilera, Mary J. Blige, and 50 Cent. It doesn't ring a bell. Okay, anyways, so this is another example of a semi-supervised clustering. And then let me introduce briefly, hopefully, for another research of mine. So this is the topic modeling result based on also the matrix factorization. But here our setting was, we set our problem as we are initially given two different data sets. So first and the second data set, and then we want to jointly cluster them. So if we have maybe 100 data items as data set 1, and then another data set having maybe 150 data items, and then the first thing that we can consider to perform clustering is just we aggregate them into a single cluster, a single data set, and then perform the clustering. But here we viewed this problem a little bit differently. We just cluster them into maybe 5 clusters and maybe also another 5 clusters. I mean, still separately, but here, maybe two of them are constrained to be the common one. Okay, so it is clustered into 5 clusters, and also the second one is 5 clusters. But those two, the common clusters will contain data items coming from both data sets, but the clusters shown over here, which is corresponding to A minus B and B minus A, okay, for these clusters, those clusters should not contain any data from the second data and so on. So I want those clusters to be really exclusive. I mean, in terms of their meaning, I want the clusters to be exclusive to the first data set, and also another set of clusters really exclusive to the second data set. So this is one example. So we can think of the research papers as our documents, and then these are all papers published in the data mining venues, and then I just split them into two sets, where the first set is those papers published before 2005, and another data set published after 2006. So in this case, we can consider In terms of the topic modeling or soft clustering, we can consider the common topics or common clusters that encompasses the two data sets, and then those two topics are shown to be these. So outlier detection and clustering itself, and those two topics are the clusters existing in both data sets in earlier papers and a little bit recent papers. So it means the clustering and the outlier detection is a consistent topic that are studied. Okay, and also as an exclusive topic, only appearing in the first document or those papers published before 2005, and then association rule mining and frequent pattern mining and so on. Those topics are more dominant one, only appearing in the earlier documents or earlier papers, and more recently social network and the large scale graph and the database, and these are more recent topics. So so the paper title is something like this: compare and contrast between the two sets of the documents. And so it is like done joint topic discovery. And so I'll briefly introduce or explain how I formulated. And we have these two different data sets and as a term document matrix, and they are we are performing the topic modeling basically separately on these two data sets. Okay, so far so good. But here so W1 is considering like the 5 topics, and then we have 5 columns on W1, and also let's also 5 topics for the second topic, second data set. And then here let's assume that it requires these hyperparameters in terms of the number of common topics and distinct topics. So suppose those 2 topics are actually the common topics across these 2 data sets. And then here we just call this part as W1 and C, and the topics belonging to the first data set and common topics. And then this part is W2C. Okay, and then we can simply give this Frobenius norm in terms of their differences. Okay, so that's how we can impose those 2 columns of the first and the second topic matrix to be close to each other. So this is another regularization to obtain common topics. And then let's think of this second term. So in this case, so it's a really small, but this part is W1D, and this part is W2D. And then let's consider this guy, W1 transpose, W1D transpose W2D. In this case, what will be the size of this part? So it's like, so we just transpose it and then multiply that, right? So we set 3 topics from the first and the second data sets to be as far as possible, so that the clusters, for example, cluster centroid should be really far apart. Okay, so we still apply the inner product based similarity, and so it is giving us 3 by 3 matrix, and this is a pairwise inner product matrix between the 3 topics from the first data set and the another 3 topics from the second data set, right? And so we obtain this 3 by 3 matrix that indicates where each element indicates the pairwise similarity in terms of the inner product between any pair of the 2 topics from any pair of the topics from the 2 data sets. Okay. And then in order to minimize the similarity based on this inner product, and then we can apply this Frobenius norm as well. But I think that is I'm not sure if it is a really Frobenius norm, but yeah. By the way, if we have this matrix and then you guys know how to compute the Frobenius norm, right? Take the differences and compute their squares and sum them up. But what if we consider their one norm, basically 0.1 and their absolute value, and also 0.1 coming from here, and then 0.5 and 0.2 and so on. So this is basically one norm that we are familiar with, right? But this guy, can we say it as a one norm? So this is a clear, this is wrong. So I had to recently I had to ask my student to change this part for already submitted Camerary papers, and then so for matrix one norm it is a completely different one. So so it is called the 1-1 norm. Okay, so this is called 1-1 norm. And what about the 1-2 norm, or maybe MN norm or something like that, or PQ norm or something like that? So that is I forgot the order, but this 1-1 norm or maybe 1-2 norm, and then we basically compute the I'm confused whether the row comes first or column comes first, but let's assume column comes first, and then we basically compute the L1 norm of each column vector. Okay, and then here point so this is the L1 norm of the first column, and then the second one is this guy, right? And then once computing it, and then we just compute their L2 norm. Okay, so that is like 1, 2 norm. I'm not sure row comes first or the column comes first, but so those two values are like first computing the column-wise L1 norm, and then once obtaining them, and then we just compute their L2 norm by using those as an elements. Okay, but anyways, so I'm not sure if I used the Frobenius norm or 1-1 norm, but 1-1 norm is another possible choices. Okay, so here so I just try to minimize the squared sum of the matrix element here. Okay, so we just sum of the squared inner product values between any pair of the topics. Okay, so that's how we impose or encourage or edit the regularization to make the topics corresponding to this in this part to be as far as possible to each other. Okay, and also in the case of a non-negative matrix, the inner product, so let's consider like the inner product between the two vectors, and suppose these two vectors are non-negative. Okay, so there is no negative element, and then of course the inner product can be positive infinite, but what is their minimum possible value of their inner product? inner product will be at least equal to or greater than 0, because we are only having non-negative values. And also, what's the meaning of the inner product being 0? So in that case, if some non-zero values are found over here, 0.8, and then how can we achieve the inner product to be 0? Then this value should be 0 over here, right? So at least for those matching entries, at least one of them should be 0, considering non-negative values, right? So in the case of topic modeling, what's the meaning of it? Suppose these two are the two different topic vector, chosen from the two data sets. And then that means, okay, so if the first data set has used this term in that topic with a non-negative value, okay, and in that case, the second data set and this topic from the second data set should not use this term at all, right? So if you remember, right, and then in this case, because this guy has the largest entry, and so this topic will have the major meaning related to this keyword and this keyword and this, right? So basically in this case, we are involving all the keywords to define this first column of topics, right? But in order to achieve this 0 inner product between the other two the other vectors, and then at least some of them should be set as 0, so that we can allow non-zero values in the second topic, okay, to make the inner product to be 0, right? But it's all done in the form of this soft regularization. So their inner product doesn't need to be strictly 0, but their inner product should be minimized as possible. As much as possible. Any questions so far? 네.
W랑 W 원소가 음수가 되면
네.
내적을 쳤을 때 0을 가까워질 수 있게 이제 코사인이라도
네.
하는
그렇죠.
양수일 때는 반대로 생각하는 말씀이시죠?
양수일 때는 네.
음수를 가질 수 있을 때는
네.
내적이 값이 작을수록 두 벡터간 유사도 높다는 건데
아, 네네.
양수인 경우에 저같이
네.
다른 걸 말씀해 주시죠.
그러니까 이제 내적이 우리가 양수가 되면 될수록 큰 거고, 이제 뭐 예를 들면 그러니까 일반적인 이제 음수랑 양수랑 다 있는 그런 벡터에서는 내적의 범위는 기본적으로는 뭐 마이너스 무한대에서 소프 무한대잖아요. 그리고 이제 놈 혹은 이제 그 벡터 랭스로 노멀라이즈를 하면 이게 이제 마이너스 1에서 1 사이로 딱 바운드가 되는 거고. 그래서 예를 들면 뭐 이 마이너스 1이라는 것은 사실 이거는 어떻게 보면 이게 벡터가 완전히 이제 반대 방향에 있다는 것이기 때문에 이게 사실 그 코사인 시밀러리티 측면에서 가장 작은 거인 거는 맞지만, 그렇지만 이게 좀 이게 하나하나 디멘전이 어떤 뭐 예를 들면 뭐 이런 벡터가 있다. 그럼 이 말은 이 키워드가 되게 많이 나타나고 이 키워드는 별로 안 나타났다, 약간 이런 뜻이잖아요. 타픽으로 해석을 하면. 그럼 이거에 이제 그러니까 뭐 마이너스까지 허용을 한다면 이게 이제 이너 프로덕트가 제일 작아지려면, 코사인 시밀러리티가 제일 작아지려면 이렇게 돼야 되는데, 이렇게 된다는 말은 이 키워드가 여전히 나타나되 뭔가 제일 마이너스 쪽, 이건 말이 안 되긴 하지만 이게 하여튼 그 디멘전의 값이 여전히 크되, 절대값으로는 여전히 크되 이제 마이너스 값으로 많이 나타나고, 이 디멘전은 얘가 별로 안 썼잖아요. 그러면 이제 얘도 별로 안 써야지 하여튼 마이너스 1이라는 그 가장 그 이제 디시밀러한 그 코사인 시밀러리티 중에 가장 작을 수 있는데, 이게 사실 많은 경우 우리가 이제 코사인 시밀러리티도 그렇고 뭐 할 때 이제 0을 우리가 달성할 수 있는 어떤 코사인 시밀러리티로서 가장 작은 값이다라고 생각을 한다면, 그리고 이게 난제로 벡터일 때는 실제로 마이너스가 될 수 없으니까 그게 이제 이 0이 이제 달성할 수 있는 가장 작은 코사인 시밀러리티 값인 거고요. 그러니까 뭔가 개념이 바뀌거나 그런 건 아니고요. 이 어떤 값의 범위가 이제 0보다 크거나 같다라는 이 어떤 우리가 스타팅 포인트로서의 우리의 컨스트레인트 때문에 이제 그 이너 프로덕트나 뭐 코사인 시밀러리티도 당연히 뭐 이제 마이너스 부분은 없어지고 이제 0에서부터 시작이 된다는 것이 되고, 그렇지만 이제 여전히 뭐 이쪽으로 가면 갈수록 더 시밀러리티가 커지는 건 맞아요. 근데 제일 작을 수 있는 이 값이 여기서는 뭐 이런 거였는데 여기서는 이제 이런 거잖아요. 이게 90도가 돼야 되니까. 그리고 이 말은 사실 이쪽 저쪽 뒤쪽으로 가면 안 되죠. 사실 난 네가티브 영역은 1사분면이에요. 그렇죠? 1사분면이고, 그러면 얘가 뭐 하여튼 뭐 그럼 이거를 보면 이거는 무슨 소리냐면 이제 얘가 쓴 디멘전, 얘가 이제 첫 번째 디멘전은 일단 썼고 두 번째 디멘전도 썼어요. 약간의 값으로 써갖고, 그래서 얘가 도망갈 데가 없는 건데, 어쨌건 0을 달성하려면 어느 디멘전을 얘가 난제로 값으로 쓴 게 있으면 그 디멘전은 이 내적이 0인 값을 달성하고자 하는 또 다른 벡터는 그 디멘전은 못 쓴다는 거잖아요. 그래서 그게 이제 타피 모델링 측면에서는 이제 각 디멘전이 이제 키워드들이니까 어떤 키워드들을 이제 적당히 그러니까 값을 뭐 크든 작든 뭔가 난제로 값으로 활용을 했다면, 그러면 그 타픽에서 쓰여진 키워드는 그 그러니까 두 번째 타픽에서는 사용할 기회를 잃어버리는 셈이 되는 거죠. 그래야만 이제 완벽한, 그러니까 아이디얼한 상황에서 내적이 이제 0이 될 수가 있다는 그게 되고. 네. 근데 뭐 이렇게 되지는 좀 않고, 네. 일반적으로는 이제 한쪽에서 크면 이제 딴 쪽에서는 이제 작게, 뭐 한쪽에서는 작으면 딴 쪽에서는 조금 커도 되게, 이런 식으로. 그러니까 그게 무슨 말이냐? 타픽 모델링 측면에서는 디멘전들이 서로 오버랩이 안 된다는 뜻이 된다는 거잖아요. 내적이 0이다라는 말. 디멘전이 오버랩이 안 되기 때문에, 디멘전이 오버랩이 안 되는 말이 뭐냐? 각 타픽의 이제 그 의미를 결정짓는 그 키워드들이 이렇게 겹치지 않는다는 뜻이 되잖아요. 네, 그러니까 이제 타픽 모델링을 할 때 어떤 두 개의 타픽이 애매하게 겹치는, 그러니까 애매하게 뭐 비슷한 키워드들이 많이 좀 등장하는 식으로 여러 타픽에서 그게 좀 나타나서 이게 구분이 잘 안 되는 경우는 이런 orthogonality constraint 같은 경우가, 네, 굉장히 뭔가 좀 타픽 간의 오버랩이 없는 측면에서 도움을 줄 수 있다는 거죠. 또 다른 질문 있나요? Okay, and then in this example, so let's consider the actual optimization based on this block coordinated set. So yeah, even though we discussed about these regularized version, for example, like this kind of regularized version, and also are there any regularized form? Yeah, this is also another regularized form. So yeah, in general, we can freely set our objective function, okay, by using our imagination or our creativity. We can actually put whatever additional regularization term to improve our result in our own manner, okay? But setting up our objective function and actually coming up with a particular algorithm that can solve this given objective function is two different things. So in general, if we set, for example, if we set this guy as 1, and then the algorithm will become really complicated because we have to handle the root over here, right? And also, in the case of a non-negativity constrained least squares where I also mentioned about this active and passive set and so on. So if we do not know about this active set based method, and then it is impossible to devise some of the algorithm to solve our non-negativity constraint, this matrix factorization problem at all, right? So we can freely impose some of the meaningful constraints and also another regularization terms in whatever forms, but coming up with the algorithm itself to handle this optimization criteria is a completely different one, okay? So let's see. So in this case, let's also consider the block coordinate descent based algorithm. Okay, so this is already published paper. So we also proposed the algorithm to solve this problem based on block coordinate descent. So this is a really possible one to come up with optimization algorithm. So yeah, we approach it. We propose the algorithm based on 2K block based block coordinate descent or outer product based block coordinate descent. Okay, so in this case, so let's consider these two terms, and then for example, let's consider this part as our variable. Okay, so this guy is fixed at this point, right? And then yeah, in general, let's consider this guy, and maybe WR, that we saw in the weekly supervised version. In this case, we have W over here involved in these two different terms. And then it is written as this form. To have like ax minus b, which is similar to like least squares form. So I think we I showed similar manipulation like this, but here, so we are over here, and then here we have identity matrix in W, and WR, right? So we have H transpose and W transpose minus A transpose. Then we have, so let's just apply W transpose over here. Right? So we have identity matrix over here, and so we can make it as single Frobenius norm case. And then we have H transpose and identity matrix, and then W transpose minus A transpose WR transpose and Frobenius norm squared. Right? So in this case, from the partitioned matrix product perspective, then it is H transpose, W transpose, and I and W transpose. Right? So it will have these two parts. Right? And then we just subtract it, and then we have this part minus this and this part minus this, and so we can obtain a single matrix factorization case where we have this part and this part are all known and this part is an unknown. Okay, so that's how we combine. So here, we have an alpha over here. So we have square root alpha by just putting it into this identity matrix. Okay, so we viewed this kind of case when studying the regularized least squares problem and their normal equation derivation, right? So we can apply these regularization terms and then come up with a single unified formula. So likewise, this part is also manipulated in the exact same manner. And what about this guy? In this case, yes, in this case, as long as we have like ax minus b, then it's Frobenius norm. Okay, so suppose this guy plus cx minus d Frobenius norm and so on, and then it can be really written as a and c and x and b and d, right? And a single Frobenius norm can be written from the sum of these two Frobenius norm case, right? Any questions? Can you guys understand? 이해 가죠? 네? So just to help you understand, so this guy times this is this, right? And this guy times this is this. And this guy times this is this element, right? And then this guy times this is this element. So we just arranged it in a single column. And then similarly, this guy times this guy is some element over here, and this guy times this is somewhere over here, right? So that way we can have this correspondences in the big Frobenius norm case. And so how we manipulated this part is based on like ax minus b. So we have ax minus b, where a and b are known, and the cx minus d. So that way we just put them or concatenate them in a row-wise manner to obtain this a single one. Okay, and then from here, this guy can also be represented in this form. So this guy and the Frobenius, when considering this a Frobenius norm, then we can also represent it as this form, W2D transpose W1D, right? So it's similar to like A transpose B is the same as B transpose A. Although this matrix and this matrix is totally different one, but in terms of a Frobenius norm, we will just take the square of each element and then sum them up. So from the Frobenius norm sense, this Frobenius norm of this matrix A, this guy is the same as the Frobenius norm of its transpose version, right? So we can easily switch them, and that's why that's why I was able to rewrite this part into this transpose version, right? So A minus WH, we can freely change them the order, and then we just apply the transpose on this representation to obtain this, right? Any questions? 이해 가죠? 그러니까 뭐 1, 2, 3, 4, 5, 6의 프로비니언스 놈이나 뭐 1, 2, 네, 1, 2, 3, 4, 5, 6의 프로비니언스 놈이랑 똑같잖아요. 트랜스포즈 해도 뭐 매트릭스 프로비니언스 놈 똑같죠. Okay, then here, yeah, we can freely change it into the transpose version over here. And then it can also be viewed as like ax minus b. So a is this guy, and b is what? B is zero matrix in this case. So we can concatenate them in a row-wise manner to form a single unified Frobenius norm kind of case, and then we can apply, yeah, two-block coordinate descent to utilize this non-negativity constraint least squares, and then yeah, 2k block coordinate descent framework as well. Okay, so that was it about this NMF. Okay. And then the next thing is spectral clustering, and this is another clustering algorithm when given the graph data. Okay, the graph data. So there are many different applications of using this graph data. Then if we are given the feature vector representation, and then we also discussed, yeah, we already discussed about how to change it into the graph, yeah, form. So yeah, the one popular method is to use the Gaussian kernel to change the distance between the two data points into a similarity, right? And so that way we can obtain the pairwise graph matrix or similarity matrix using this Gaussian kernel. And yeah, suppose yeah, but in general, in general, if we are given a graph of 4x4 data, 4 data items, and then yeah, some values are given, but some other values may not be given as well, right? So in this case, so originally the graph is given for our data sets or data items, but here between 1 and 4, the edge is not defined at all. So in this case, we can view them. We can view that case as having zero similarity. Okay, but anyways. So this is the graph that we are given as the pairwise edge relationship. So if we have a large value, and then it will have a large similarity. So in the case of graph clustering, yeah, we basically cut them into multiple pieces, right? But here, the notion of the good clustering or the good quality in the context of a clustering is that if we cut them into these two pieces, okay, and then within each group, the similarity should be as high as possible or as large as possible. So those data items belonging to single clusters, so they should have a large similarity between any pairs in general. Okay, and also between different clusters, those similarities existing between the data items belonging to different clusters should be minimized as much as possible, right? So in this case, it can be viewed as like graph cut kind of problem. So we are given this graph, so we kind of cut some of these existing edges to form the given number of groups. Okay, so if we want to obtain two groups as a clustering result, and then it is reasonable to cut over here. So from this perspective of cutting our graphs to obtain multiple pieces, and then one potential criteria to think of in this graph cut as a clustering algorithm is really to consider these edges that are cut. Okay, so the cut measure between these two groups of an A and B. Yeah, so when cutting these data items into these two groups, and then this cut measure is simply defined those edgy weight, the sum of edgy weights that are cut. Okay, and so minimizing this graph cut or this cut measure is called min cut algorithm or min cut graph clustering method. But here in this case of a min cut, it has some limitation. So in this case, we may have, we may think of, we really have large edgy ways around these gray colored point, and then also high edgy ways between these brown colored point, and then the optimal cut would be somewhere over here. But here in this graph, how many edges do we have over here? We have 1, 2, 3, 4. Although these edgy weights are maybe 0.1, 0.2, 0.1, and 0.05, and these are all small values, and the cut measure will be simply the sum of them, right? And then what is the sum? 0.3, 0.45. So this is the total cut that we had to sacrifice, right? But what if this guy is really closely related, and 0.2 and 0.2, although these two edgy weights are not that high, but suppose this guy is having a relatively large weights, but with a few number of other data items belonging to the same cluster. So in this case, simply because this guy has a small number of edges, small number of edges, and then if we cut over here, and then the cut measure is only 0.5. So if we only consider this cut measure to minimize, and then this cut or this cut, is a better cut or more optimal one than this cut. Okay, so this is clearly not what we want. So we can think a little bit better than just only considering this minimum cut. Okay, so the next algorithm is called normalized cut. So we basically use the normalized version of this cut measure. Okay, so this is the definition of the normalized cut. So these are cut measures that we had to sacrifice or minimize, but this cut measure is actually normalized by the volume of each cluster. So in this case, so the volume is the sum of edgy weights belonging to the single cluster. Okay, so in this case, we have the volume coming from the first cluster and the second cluster, and so this 0.45 that are cut measure over here in this case is divided by the total edge sum of the total edges within the cluster 1, and suppose that is maybe 5.4, which is the sum of an edge weights, and then the sum of an edge weights in the second cluster that are involved in this cut is maybe 4.8. Okay, and so these cut measures are divided by the respective volume of each cluster, and then we consider this as normalized cut. So in this case, even if we have a smaller cut in this case and really large volume in the single cluster, right? And so it is like maybe like this measure, which is really small, but so far so good. But here this cut measure should be divided by the volume of the second cluster. And so in this case, if we don't consider any self edges, and then it should be really divided by 0, which will give us an infinite. But yeah, let's consider like the cut of like these two. Okay, so in case of having this small sized clusters, and then their edge weights is maybe 0.3, and then we will divide this cut measure by 0.3. And so at this point, this cut measure is really exaggerated or expanded. Okay, so overall, this measure may be better than this measure. Okay, so using this measure as our criteria to minimize when performing the graph clustering, yeah, it is called the normalized cut. Okay, so the main effect of this normalized cut is that it actually produces more balanced partitions or clusters. Okay. And the actual algorithm to minimize this normalized cut is based on some of the eigen decomposition and something called the spectral theory or spectral graph theory. But yeah, let me first show you the example of this normalized cut. So the main application of this normalized cut algorithm was applied to this image segmentation. So you guys might be familiar with the image segmentation, but okay, so these are the image segmentation results, but this is different from the semantic segmentation. Yeah, they have something in common, in a sense that they are grouping the given pixels in a single image. Okay, but in the case of just image segmentation, but not a semantic segmentation, is not assuming any predefined class labels when classifying a particular pixel into a group. So what they do is to perform really clustering on individual pixels in a given image. So if we have a image size of 20 by 30, and then we have 60 pixels, right? And then we can think of their feature vector or their graph or similarity. So what would be the feature vector to represent each pixel? So we can think of the RGB value, right? And then also we can think of their another set of features as a location. So the first pixel is having the part of the two-dimensional feature vector as 1, 1, and 2, 1, and 3, 1, and so on. So we already have, although they are very low level, but we already have 5 different pixels, 5 different feature values, right? And then also we can think of some other features extracted from some other heuristics like SIFT and some other algorithms that we can apply as a various computer vision techniques. And then we can obtain several different feature vector representations. I mean, I'm just talking about a non-deep learning based clustering algorithm because it was published a long time ago, maybe more than 10 to 20 years ago. It's more than 20 years ago. That's when I entered my undergrad, and it was fun in that time. Anyways, So once obtaining these feature vectors, and then we can form the graph relationship by using whatever Gaussian kernels and so on, and then yeah, we can apply this normalized cut algorithm, which is just one particular graph clustering algorithm, and then yeah, we have a groups of pixels as those clusters that we set as the set of those set of the predefined number of clusters, and then these are the results. And so here, so for example, if we just use a colors as the only features, and then the pixels that are located really far apart, like over here, and maybe over here, and maybe over here, they seem to be quite close colors to each other, and so in that case, these two pixels might as well be partitioned into the same clusters, right? But here we avoid this kind of situation, or we can incorporate this spatial adjacency by using this location as features. Okay, so in terms of the location, it's like 30, 20. This is a 1, 1, and in terms of these pixels, they have a really low similarity or large distance, and so that's how we can encourage the algorithm to compute this locally close groupings of these pixels. And actual normalized cut algorithm is really based on complex and deep graph theory and linear algebra stuff. But I just give you the high-level overview of this algorithm, and we can consider this similarity graph, and we can call it as an adjacency graph. Okay, adjacency graph. And then this adjacency graph, we can also think of something called the degree matrix. So this is an adjacency matrix, and then for each node, so what's the degree of this node? So if so degree is simply the number of edges that a particular node has. So in the case of this guy, we have the degree of 4, and this guy will have degree of 3, right? But in the case of these weighted graphs, and then this degree of this node is simply the sum of those edge weights connected to this node, right? And from this matrix, the degree matrix can be computed by just simply simply adding these values. These two are, in the case of symmetric matrix, those two values will be the same, and so the sum of it can be placed over here as a diagonal entry. So we can consider this degree matrix. Okay, and then I don't have much insights or technical or knowledge about the graph theory, but the graph theory is involving really heavy math, and this Laplacian matrix defined as simply the difference, subtraction from this D of adjacency matrix. Okay, and then we will have a diagonal element over here, and then we all have now negative entries on the off diagonal part. So simply degree matrix minus adjacency matrix. Okay, and then this matrix has really interesting property. So basically those values, the sum of it is placed on the diagonal. So you can kind of intuitively think that off diagonal part can never beat diagonal element, because the sum of off diagonal part is always shown as the diagonal element. So that way, this guy has some interesting properties in terms of their eigenvalues and eigenvectors. So yeah, eigenvalues are all non-negative real numbers, which means this guy is positive definite. Okay. And due to the symmetry of this matrix, the eigenvectors are orthogonal. And this one also has trivial eigenvectors, I think. It is all ones, I think. So if you just plug in all vector of all ones, and then that is the eigenvector of this matrix due to the formation or how we formed this Laplacian graph Laplacian. Yeah, and then yeah, we can kind of normalize it in this manner, and then yeah. So it's really deep into the linear algebra and this spectral graph theory, but yeah, I don't think I will cover this more deeply because yeah, it's really specific to particular algorithm, yeah, related to this graph theory. But overall, let me just point out the main criteria, which is the graph, the normalized cut. Okay, so in order to maximize this normalized cut, okay, so how can we obtain the optimal partitioning or optimal cut of our nodes into multiple groups of nodes or groups of pixels, for example, and then considering their normalized cut measure and then minimizing it, and how can we achieve this optimal partitioning to minimize this normalized cut? Okay, so that is all related to this graph Laplacian, and then yeah, we apply the eigen decomposition on this matrix, and then if we have a 100 nodes, yeah, maybe 1, 2, 3, 4, 5, 6, 6 by 6 as a graph Laplacian, and then applying eigen decomposition, and then we can sort the eigenvalue and vector pairs in a decreasing order of eigenvalues. Okay, and then we will obtain so here we have to choose some of the major eigenvectors. So yeah, just like applying the PCA. Okay, PCA, I mean here if we want to have three groups, and then we just choose three largest eigenvalues, okay, and then we will have their corresponding eigenvectors, and eigenvectors are in this case 6-dimensional vectors are each of our eigenvectors, right? And then we have like these three eigenvectors that are all 6-dimensional vectors, right? And then we can consider this 6 by 3 matrix, right? And then I'm just giving you the sketch of how this Laplace normalized cut algorithm works, okay, without much of a justification, okay. So once obtaining graph Laplacian and applying the eigen decomposition, and then choose the k most largest eigenvectors, okay, and then here we now consider these 3-dimensional vectors, 6 of the 3-dimensional vectors, and these 3-dimensional vectors is your feature vector of the data item, okay. And then using these 3-dimensional feature vectors corresponding to each of our data items, and then we simply perform k-means on that, okay. And then it will give you the partitioning that will optimize the graph cut, the normalized cut measure. And those new 3-dimensional representations coming from the 3 largest eigenvectors, okay. So yeah, why does it give us like a good representation when just simply performing the k-means, and then those feature vector representations can be viewed as a kind of new representation that will just naturally reveal those representations that maximizes this normalized cut criteria. I mean minimizes the normalized cut criteria. So that is the overall or high level kind of, process of how this normalized cut algorithm works. Okay. Any questions so far? Okay, then that's it for today, and that's it also that's the end of the big topic of a clustering, and then we will move to dimension reduction next time. And also, by the way, alternative projects related to EM, that you can do instead of your project, it will be posted later tonight. So I just shamelessly copied one of the homeworks from some other university's website. Okay. So that is about like finding out the genes, gene sequences and their mutations and so on. Hopefully it will be fun. Okay, thanks.